Curtis and John have been working on the theory and the literature on data analytics and big data, and so they're going to share with us what they've learned on that and some of their projects and the things that they're doing. Curtis is working with Dr. Graham, and John is working with myself on projects in this area. So we'll turn the time over to you guys.
Okay, thank you. So we figured we couldn't get enough of John, so we brought him back. John and I are taking a directed study project class this semester. We're both doing dissertations that involve data analytics, and we thought to help us better know to talk the talk, we better get into it and seeing what the discussions are in education. And we've been invited to present some of the things that we've been learning. We hope that as you listen to our presentation today, you'll be able to find some applications into the work that you're doing. Because big data can be a powerful tool for both research, evaluation, and for instructional design. So I think there's some applications to everyone here. Some of the terms you hear when it comes to big data, you hear data mining, data analytics, learning analytics. And a lot of people say these are all referring to the same thing. Other people believe that there are important differences. Some of the differences that people point to, they say it's not big data if you're not dealing with a large data set. Of course, the question with that is what is large? When is it no longer large and is it small? Other people say an important difference is whether the data that you get is technology derived. So we have systems that are capturing a lot of information about how users are behaving, click streams, page views, and they say it's not data analytics or data mining unless it's technology derived. But I think really technology is important to making big data possible and easy, but it's definitely not necessary. Other people say that it's not data mining or data analytics unless you're going into it to discover models or knowledge from the data. And I think this is definitely a key definitional point, that when we're doing data mining, we're going into it to explore what's there. We have some notion of what may be there, but really we're there to see what we can find. Another important point that people bring up is that it's not data mining unless you're using automated or semi-automated computational analysis. So in other words, big, powerful statistical tools that do some of the analysis for you. This is definitely helpful to doing big data and data mining, but I wouldn't say it's necessary. But depending on who you ask, these are some of the definitions that you'll hear when it comes to big data or data mining, data analytics. I've been reading a book this semester called Big Data, A Revolution, which if you're interested in this topic, super useful. The argument that the authors make in this book is that big data is more than about dealing with a lot of information, that it's a new paradigm of how we can look at the world, the types of information that we're collecting, what we can learn from that information. And what's helped me to better understand that paradigm is to compare big data to more of our traditional empirical approach to research. Both with big data and research, we're asking questions, we're gathering information, we're trying to interpret the information we find for useful answers. But there's some big differences between the two. With traditional scientific empirical research, we're focusing our data gathering. When we make surveys, we can't ask people a billion questions. We'd like to, but people just aren't going to answer all the questions that we give them. So we've got to focus on what we think is most important. But with big data, it's a totally different approach. We're trying to get as much information as possible. And so maybe we don't turn to surveys to get that information, but we're looking for data that's already available and accessible that we can turn to. One example of this comes from Matthew Fontaine Maury. He was a U.S. naval officer in the mid-1800s, and in his naval experience, he began to notice that there wasn't really a science to sailing, that a lot of people had their own intuition or notions. There were a lot of ideas out there, but he didn't feel like there was a science to actually sailing. But he noticed from his own experiences that there seemed to be a lot of predictable patterns about the ocean. Waves came in at certain times in certain ways during the day, and different ways at other times. The wind blew in a certain direction at some point of the day, and then it changed directions at other times. And he wanted to answer this question, is there a science to sailing? So he began to gather as much information as he could. He turned to maps, he turned to journals, he turned to books that were published on the subject, and then he began asking that captains capture more information about their voyages and share it with him. And he ended up gathering over 1.2 million data points and analyzing that information. I mean, this is a lifetime work, and published a book on it. And basically that book details ocean currents. He was kind of the guy who discovered ocean currents. And his work cut most voyages across the ocean by a third of the distance and a third of the time. And his work is so important that we still use those same routes today. But the idea is that we try to gather as much information that's already out there and see what matters, what relationships exist that can help us do certain things. Another key difference between research and big data is with research where we're trying to do what's feasible and we're focusing, generally we're looking at a sample of the population and then we're trying to generalize what we learn about that sample. Whereas in big data, oftentimes we're dealing with so much information that we are looking at full populations. For example, when Google is looking at how users do search terms, they're not just looking at a sample population, they're looking at all Google users. And that is a lot of information that has provided some pretty interesting stuff. Another key difference between research and big data, research is causation is very important to research. We want to find cause and effect. When we do studies, we try to control as much as we can so that we can point out what is causing the things that we're seeing. Whereas in big data, because we're dealing mostly with historical information, we don't really have control over the context. And so what we have left is correlation. But with correlation in big data, it becomes very important. An example of this is with Walmart. Walmart has been gathering information about the purchases that people are making from cash registers, their inventory data, and they've just been gathering this from all their stores for years, and they decided to start analyzing it. And one of the weird connections that they saw was that at some point in some stores, there was a huge increase in the sale of strawberry Pop-Tarts, almost 7 times the normal amount that they normally see. And they tried to investigate why this was happening. And they noticed that it happened at certain stores just at some bizarre time of the year. And what they found it was the stores that were in the paths of hurricanes. And when a hurricane was predicted to come through, strawberry Pop-Tart sales would go up the roof, along with flashlights. And so what they started doing was stocking those stores and watching weather patterns to make sure that they had enough strawberry Pop-Tarts in the stores. And so this is a correlation. Obviously we can't find causation here, but this correlation became very powerful and meaningful. And that's the idea with big data, is that correlation can have a lot of value.
I thought you were going to say Pop-Tarts cause
Only in Walmart.
This approach to information has allowed Target to identify from purchases who to send promotions on pregnancy and baby items. It's allowed UPS to identify what are the most efficient routes to deliver something. This is providing a lot of useful information to businesses, and it's now trickling into education. What can we do with all the data that we have available to help people with learning or to help schools run? So I'm going to turn the time now over to John, who's going to look at the history of big data and education, and then we'll get into some applications.
So I'm going to talk a little bit about big data as it applies specifically to education. I'm going to talk a little bit about the timing, about some of the factors of growth. Where's the growth coming from? I'm going to compare it a little bit and contrast educational data mining versus learning analytics. Those are two different entities, if you will. They have two different conferences, two different journals, and I'll talk a little bit about differences and similarities between these two. And then talk a little bit about resources and tools, specifically for big data in education. And in fact, Curtis's previous slide reminded me, I don't know if you've heard about this or not, but there was a Target effort that was sending, what was it? It was, Target was, just like you said in your slide, Target was sending a young girl, a relatively young girl, some information about some pregnancy items. And the father finally had enough and called up Target and said, this is not for me. She's my daughter and she doesn't need this. And it turns out that she was pregnant and he didn't know about it. So Target knew before the daughter's father that she was expecting. And that's kind of an interesting one where big data sees all, maybe, I don't know if that's bad or good, but kind of an interesting example. So the beginning of educational data mining started around 2009 formally with the launch of the journal. There were some conference series in about 2008, some workshop series in about 2005, and some earlier stuff before then. But that's relatively, that's recent. This is not very old. These are new beginnings. Learning Analytics was a little bit later. The Journal of Learning Analytics is just about to come out. They have a website up, and they have not printed their first issue yet, but that's in work. There's been some special issues of Learning Analytics in the American Behavioral Scientist, 2013, and some others there, 2012 and 2011. And there's some other attention that's getting bought out in terms of learning analytics, in terms of big data, and some other conferences as well. But overall, my point here is that it's pretty new. This is all pretty new stuff in terms of using big data in education and the research implications and tools. So let's talk a little bit about growth. In terms of growth, well, the quantity of data has increased, right? And Ryan Baker, one of the educational data mining, I think he's the president right now of the International Association of Educational Data Mining, he suggests this is not Google big, this is not Human Genome Project big, but it's big relative to education. He says there's papers now that have research with tens of thousands of students as the ballpark, you can ballpark that. There's growth in online learning, there's growth in interaction data. Both of these are feeding some of the demand for, well, what do we make out of this data? And there's new data capture technology. There's wearable sensors, there's eye tracking that's become cheaper to do and more robust, more reliable in some ways. The second big bullet here is improved data formats. So no longer is there kind of anybody choose your own data format to capture these things, but the data formats are actually starting to standardize. And that's kind of a good sign, where exchanges of data can happen more freely. There's less data needed, less time needed to transform data and to prepare the data from when you collect it to when you analyze it and start looking at it for usable information. Of course, there's advances in computing, just the idea of the architecture of computers and computing itself, as that improves, that helps benefit collection and analysis. And then there's the sophistication of analytic tools. MapReduce was developed at Google to analyze and to handle some of these very, 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 very large data sets. And that spawned another creation called Apache Hadoop, which also handles some of this very, very large data storage and analysis on relatively cheap hardware, which was kind of the other idea, is they wanted to be able to manage all of this data relatively inexpensively. Instead of having specialized hardware, they modularized it differently at the software level so that you could use cheap hardware, and they account for the fact that if one piece of that hardware, one node goes down, then MapReduce and Apache Hadoop can account for that. And it can say, okay, this guy's down, let's spread the analysis somewhere else. So those kinds of things have helped with the growth. Let's talk a little bit about EDM and LA. At the very high level, this is from Siemens and Baker, 2012. Both communities have the goal of improving the quality of analysis of large-scale data to support research and practice in education. But there are some differences. Educational data mining has considerable greater focus on automated discovery. And learning analytics has a considerable focus on leveraging human judgment. So this is how we're discovering the data, right? This is one way of saying, kind of what Curtis was saying before too, where there's automated or technology that's actually collecting and discovering the data. And then there's more human judgment side, which is the human that's saying, this is important, this is important, and this is important. What's interesting about this, and they say this in the paper as well, these are not hard lines between the two groups. This is just one of the things that they've seen as one of the shades of difference between the two groups. So there is some overlap here. It's not like one does not do the other, but there's a tendency for one to the other.
So would the Walmart example be automated discovery?
In terms of the Pop-Tarts and the hurricanes?
Yeah.
Right. They're collecting that automatically. That's becoming automated. And then how they do that, how they interpret that was kind of the human judgment side, right? So what does this mean and what's the correlation? It would be interesting to know if they did that without any human judgment, or if, what degree of human judgment
Yeah, they did
was
use
involved.
human judgment. Figure out that it was the hurricanes that was the relationship.
Yeah, and that's a good example of where there's a little bit of both.
I wonder, could you possibly do either without the other? I mean, how can you do automated discovery if you don't think about it?
Yeah, exactly.
Well, on that, on automated discovery, there's been some instances where the computers have been told, when you see this, do this, and that's become a problem. So they usually stop that kind of thing, like they crash the stock market kinds of things when they do that automatically. So they often, like this other one, they see the data, but they don't want the computer to automatically order more Pop-Tarts. So they say, hold it, let's make a human judgment there. They haven't got quite to that point in some of these things.
Yeah, especially if the hurricane changes direction. You don't leave Pop-Tarts.
I'm wondering if this has to do with, oftentimes when you collect large amounts of data, there are inputs that are correlated to the outputs that we might have never even considered, never even considered, right? But the machine that in the educational data mining, they can discover what those correlations are, but then a human helps to actually determine what the causal correlation is. So in the case with the Walmart, the data mining actually identified what the correlations were, and then a human went in, or the machine identified the patterns, and a human went in and said, what could be causing this pattern, and came up with the causal inference,
One thing too with human judgment is how can we display the findings in a way that we can act on it. So a lot of the human judgment part is visualization.
I agree.
Is there anything different, between these two related to real-time analysis of data versus kind of post-hoc analysis of data?
That's a great segue. A lot of the EDM work, because it's automated discovery, they're trying to put that back into automated intervention, automated adaptation, right? That's kind of a natural flow, if you will, of how they're going about it. So this is one of their sub-bullets, which says there's also this tendency to get to your point, which there's more of the automated adaptation in EDM versus LA versus learning analytics, whereas the learning analytics is more the informative power, instructors and learners, and then they intervene, right? Then they are the ones that choose how to do that. Again, these aren't hard lines, but these are some things that they've seen, some patterns.
I went to a conference this last summer for educational data mining, and they were describing automated tutoring systems that are being used by millions of students, mostly on the East Coast, but all over. And this is it's automated adaptation is what it is. It's intelligent tutoring systems they'll look at a pattern of responses from a student. They'll make a decision about what might be the next best thing to do, and then do that. So it's being used a lot.
I think an answer to Charles' question is that real-time analysis can happen in both, or they could be looking at much higher level information.
Yeah, that's a good point. You know, you could do real time with learning analytics, right? I mean, even an instructor who has previous data and previous knowledge about former courses or instruction could then alter their immediate behavior based on that, and it could be real time. But that's a good question.
Another indication of the size of the interest in this currently is that University of Phoenix, which is pretty big, pretty rich, just purchased a company called Carnegie Learning, which is the company that builds these one of the companies that builds these automated tutors that's being used by all these millions of students. So somehow University of Phoenix, which has in the past had a reputation for being kind of a low level, use it to survive kind of a place, is starting to explore these kinds of things. And I'm pretty sure that you'll find places like Khan Academy and others becoming more sophisticated because they already have large audiences. They will start using this. All the Coursera, all of the large MOOC suppliers, they will start using data to feed back and improve their product. And so our students need to be aware that this is great.
And it doesn't necessarily mean that we're trading the instructor for a machine. What it means is that the instructor is then freed up to do a different level of work with students. Or diagnosis happens that's more sophisticated, so instructors can be more targeted in their work too.
Yeah, there is a lot of fear on that. There's a lot of talk, especially early on. I think that's died down maybe the past year or so, 2 years. But earlier on, there was a lot of fear, a lot of pushback from that very thing. So a lot of the papers and a lot of the speeches have to say, we're not replacing anything. This is just like you said, we're going to shift the time allocation, we're going to improve the instruction, we're going to improve the diagnosis. And I think that's
Well, you are replacing stuff, but
Right.
you're replacing the human in tasks that machines are very good at and freeing up the humans to participate in tasks that that machines don't do as well.
Yeah.
We were talking about this morning. Why don't you tell them the difference between using the data to make the instruction intelligent and using the data to improve the instruction, identifying errors or problems with the instruction?
Right, we were talking this morning, we were looking at some data from students that were this is in an online spreadsheet learning course, and we're tracking individual students' keystrokes, and we can identify when they make an error, when that error is not correct, not the correct value. And because of that error identification, we have two basic options. We can try to automate some kind of intervention and program into the computer when a student types in this and they do the same thing 3 times in a row, which is what we saw this morning. Then automate some kind of intervention that pops up to the student and says, you know, it looks like you're having trouble with this. Would you like to know this? Would you like to know this? Would you like to know this? Another option would be to, instead of doing a kind of an automated adaption, would be to measure if that student's going back to the instruction, and then if they're coming back to that problem and they still have the problem, then maybe there are problems with the instruction. And there's an opportunity to then evaluate, well, how do we improve that instruction? How do we change that instruction? So does that get to your...
That's what I was thinking. That's the difference between the EDM and the LA, because it empowers the instructor to say, let's fix the instruction. You know, maybe it's not good enough, maybe it's not, like we found 25% of the students were having a problem with one thing. Maybe it's the instruction that's the problem that we need to fix, not automating it.
Charles's point about reallocating functions between the instructor and the computer is really important, and it's not just an educational issue. Back in the old days, when they were just learning about large-scale integrated circuits and computers on a chip and that kind of thing, even before then, they discovered that there were a few design decisions, that a computer could make that would take a burden of repetitive tasks off of the designer. And so they started incorporating the computer that much into the design process. That was a very small slice. And then slowly they discovered new tasks larger abstractions and new tasks that the computer can be assigned. And nowadays, 90 to 95% of a computer chip's design is done by a computer, and the humans do the strategic decision-making.
You could think about that the same, think of a large class on a basic topic where lots and lots of students are having problems with, you know, how do I add fractions that have different denominators or something like that, right? You could have a highly trained college graduate who goes through and individually responds to each one of those students, which is not a very good use of resource. Or you could have a system that identifies that this is a problem, and then you're able to create something that can take care of that resource, and then the instructor can filter off the ones who that level of intervention still hasn't worked or hasn't helped. So.
So I'm still confused. It seems like everything we've been hearing about is LA because it involves a learner or a teacher. So if EDM doesn't involve learners and teachers, why do we care about it? What does it have to do? Isn't it just a precursor to LA?
I've heard that argument made. In fact, there was a panel that I came across, and I was reading the transcript of the panel, and that was where they put it. They said EDM is really just a precursor. Well, they were looking at it from the LA perspective, and they said LA is really just a consumer of EDM, and EDM is kind of the pre-step, and then there's the LA.
They're fuzzy concept.
Yeah, and there are
There
some
is
examples.
overlap. I don't know if there's a single, you know, it may be that they're so interconnected that they're still trying to figure out where they, you know, how it'll all end up. But I've heard that very strong.
There are some examples of the automated intelligent tutoring systems, but
That's
the
true.
problem is that it's really hard to do, so there's not a lot of good ones. They've been trying to do that for 2 decades, and it's really hard to make the computer smart enough to be as smart as the human.
And it's so content specific. I mean,
Yeah.
you can't scale it.
Yeah,
You spend all those efforts on this one little math game, and then how do you apply it to writing?
yeah, and you're right, it's not scalable, and so you can spend all your time on one little problem, and then why did you spend your time on that? Because a human could have done it, you know, there is that issue, but there's a lot of interest in the EDM stuff, but it's just really hard to do.
But I like that question. Hopefully I have some examples, and maybe we'll come back to that too. See what we can dig up on that. A little bit on techniques and methods. And again, this kind of contrasts the two. So learning analytics, the K there is for knowledge. That's kind of a common symbol they throw in there when they talk about their conference. It's learning analytics and knowledge. They use social network analysis, sentiment analysis, influence, discourse, concept, sense-making models, whereas EDM is classification, clustering, Bayesian modeling, relationship mining, discovery with models, which is building a model and then using that model to create a new model, and also some visualization. Just a quick slide on tools, some of the names of the tools that they're using specifically for big data in education, analytics in education. RapidMiner,
It's free.
it's free. 5.3 is a community edition. You can download that right now. There's got some great tutorials in there. Tableau, I've used a little bit. That's very good visualizations. It's very good with diagramming the data that you have. Enterprise Miner from SAS. Weka is one from Australia that's pretty good as well. Snap is a social network analysis tool. Crunch is kind of a platform which is based off the R statistics package, which is also free. In fact, most of these are free. Tableau is free for students, actually, just this year. Weka is free. Crunch is free. Excel is pretty available. Keel is another one. And then a little bit on this data shop. So the data shop is out of the Pittsburgh Science of Learning Center. It's the Learn Lab there. It's a repository of learning analytics. I thought I'd share a couple of slides on this because I think if anybody's interested in looking at data or looking at some of these things, this would be a good repository, a good resource to know about. Over 250,000 hours of student educational software use. So what they've tracked here is they've tracked interactions that the student has with the software, with an educational software. And they are building cognitive models off of these data, and they're building student interaction models off this data. And here's some of the domains that they're in: algebra, chemistry, Chinese, English, Germany, physics, online stats courses, and some others. What's also interesting is, let me come back to that if I have time. They have this page when you go to the data shop. One of the questions that you see right when you go there is, what can I do with data shop? And it's really kind of nice because they offer you a couple of different answers. What if you're interested in analyzing process data from an experiment? What if you're interested in testing a theory of motivation? What if you're interested in applying Bayesian modeling? What if you're interested in multiple skills? What if you're interested in test my data mining method on multiple data sets? So it's actually a fairly easy way to look at both methodologies and data that's already out there, that's already been vetted, it's already been experimented on, they've already built models on it, and you can see what's out there and it's all free. Please.
So, kind of a generic question, do either of these approaches help me solve a particular person's issue? Or is it more coming up with general patterns? Like, going back to the Walmart, help me know if I can go buy a Pop-Tart when I want to, or maybe I'm trying to analyze a given student's learning issues and concerns. Can I use all of this to help a student, or is it more saying, if you fall in this range, this might be a footnote view?
Great question. I would say it depends.
That always works.
I think, I mean, the data that I was looking at this morning, for example, where 25% of the students were performing this particular problem wrong,
That's like your third one down there, right? Predicting
whether or not they know it.
percentage of students' performance as opposed to John's performance.
Right, for that one individual student, it would help them if they had predicted, potentially, right, the hypothesis that it could help if they had some intervention at that moment, and the system recognized they did this process, they have this problem, it may be this knowledge component that they're short. So in that particular case, it could help.
It's probabilistic though, right? It's not causal, so the higher, I think, the higher the probability, the greater likelihood that an intervention identified for a particular student will be able to help that student. But it's not, since it's not causal, you can't say, we know that this one
I was
will.
thinking more like for Delana, she's got all these students and teachers who are trying to do stuff. They've got lots of data on those students. Is that gonna help any of your teachers actually do something for a student in, West Valley City?
I want to go this. Clearly, here's the problem in a lot of education. You know that somebody's not performing well, but you don't know why. You have no clue because you don't have any information about that individual learner or about learners in general on that specific problem. So right now we look at, they didn't do well on the test, they didn't get that question right, but we don't know why. So the data that we're collecting is big data, collects a whole bunch of data about that so that we can understand the specific problems. So for the example of yours with the data trace that you're looking at, you say, people like you seem to have this knowledge gap. And then you can direct that instruction to help that individual student. But if you didn't have that information, you wouldn't know. You just know that they didn't get it. But you won't know why they didn't get it. It's more diagnostic because you have all of that data. And diagnosing the problem is more important than identifying that there is a problem. And you can do it with the data, you can't do it without.
One of the subtle points that's introduced, you mentioned Bayesian modeling, Bayesian statistics, which is different from classical statistics. And they work differently. One of them just treats people as a group and tries to find the mean and the standard deviation. Bayesian looks at individual actions and the likelihood of the next action, or the likelihood. So, and we have specialists on the BYU campus. In the statistics department, there's actually a movement in this direction, and some very strong people on Bayesian statistics. And it's non-trivial, but for educational purposes, it's actually the successful intelligent tutors are involve Bayesian statistics rather than mean, median, and mode kinds of things.
That's a great distinction.
Joanna,
Elena, do you have a comment?
Oh, yeah, I was just gonna, back to Dr. Williams's comment, I can see it being helpful for a particular set of students and also indirectly impacting individual students if, like Dr. Davies was saying, you could figure out the predictor, the diagnostic. Students like you have trouble doing this, and then you could have a resource for them to go to prior to engaging the teacher's time. So it would free up the teacher's time to be able to do what Dr. Graham was saying, only the things that a human being teacher can do, and letting some of the automated stuff do the rest. If that gives you quasi-answer to that question.
Great.
It almost sounds like there's a parallel between the medical field in terms of diagnosis, looking up all the symptoms and then going to a, what's it called, the pharmacology handbook or whatever, and finding an appropriate medicine that deals with those symptoms or would treat that malady or whatever. And the medical field is, in a sense, in some degrees, going in this direction as well, I think.
Computers in decision-making are much more prevalent than we realize. All of our retail stores now, I mean, that's why Target lost a lot of identity information, but they also use their computers like Walmart and like every other major retail chain to look at these patterns. And that's why you go onto the web, and if you've been off to, I went one day to look at, I think it was Kohl's. I looked at a pair of exercise pants at Kohl's, and then I decided not to exercise, so that.
We were considering it.
For 3 weeks after, and still intermittently, on the side, I'll get one of these little ads for exercise pants at Kohl's. They know exactly where you're going and what you're doing, what you're looking at. So we're not reduced to a number like we used to be feared that we were being reduced to a number. We are reduced to thousands of numbers. And those numbers are all out there.
Well, and, you know, in the business world and in the medical world, they're ahead of the educational world in terms of the data mining. I mean, businesses like IHC have been doing this for quite a while. That's how they're getting their performance increases. I don't know if you went to the devotion or the forum yesterday. He talked about some of that. The way you get improved performance at lower cost is identifying where the areas are that could be fixed, and usually that's done by looking at massive amounts of data and looking at it that way.
Can I recommend there's another, Brent James he's really famous for this. And if you have Netflix, you go look at a thing called Medicine and Money. It's about an hour and a half long, but he's on that prominently, and they show a comparison with Los Angeles health care and Utah health care under IHC, and they show the difference in the costs and the quality of service. It's dramatic.
You know, going back to this example of medicine, and the insurance industry jumps on this right away because the math guys over here that are working with them on this identified through all of this big data, people that have these kinds of symptoms and these kinds of operations are more likely to have this. And so rather than wait, they will put them on certain regimens so that they don't have this very expensive later on kind of problem. It's the same in education. When we identify students who are falling behind in certain areas, like they have a knowledge gap, they may have passed the test or we may have done a social pass, but they're missing specific knowledge things, it's something that's going to cause a problem much greater later on. And if we can solve the problem earlier on, then we don't have the big problem later on, and it saves us a whole bunch of time and money.
You don't have the compounded problem, right?
Yeah.
Let me show some examples of some of the things we're talking about. Maybe to put some more meat on this straw man that we've kind of created, this components here. One of the things that they've done, this is one study where they're looking at learning curves. And so this is an error rate, and this is the number of times that student has attempted that particular task or problem. So the first attempt, the average error rate was 40%. The red is the actual, and the blue is the predicted. The blue line is a predicted model from this Bayesian statistics category, and it's the learning factors analysis model. It's really quite interesting because it predicts what the error rate for that student at that opportunity at that content area will be. So what you can see here is the general, this is good, right? That over time, the more times the student does it, the error rate decreases. That's a good sign, right? That's kind of the classic learning curve. What they do then is they divide them down into these knowledge components. So this is for the whole assignment, or for this whole number of assignments. These are individual content areas. So for the circle area, it's interesting that it's okay. It's a little bit wobbly, but generally it's going down. Trapezoid area is going down. Square area is an interesting one, right? It starts very low, and you don't really get much of a lower error rate. The farther you go out, it gets a little bit noisy because there's less and less people that are having, that are doing it 10 times. They'll get it right earlier on, and they won't actually do it 10 times. Rectangle area is kind of closing, but overall it's kind of going down. In this particular study, which is a great read in this topic, what they noticed is that there was some over practice here. So in the curriculum and in the problems the students were doing, the teachers were having the students do this exercise too many times for that learning, for the benefit that they get of lowering the error rate. And that comes very clear in this data. What's interesting about this one is it was under practiced. The error rate started relatively high, above 50%, and they only have to 6 tries here. And the error rate is only still just below 50%. And so what they did is they did an experiment, and they said, let's change the instruction. Instead of over practicing this area, let's reduce the number of times they practice this area. Let's increase the number of times they do this and see what happens. And so they did a pre and post test. Turns out that in terms of the amount of the cognitive model the students pulled away with was the same, and the students ended up saving 20% time on the assignment. So going back to the time thing, it's kind of an interesting study where they changed the instruction based on the data, and it resulted in the same learning for reduced time, which is kind of interesting.
Please, Kenny here is one of the principals in Carnegie Learning.
Yeah, he is. Yeah, he is. He's got lots of good papers on that. All right, I'm going to turn it back to Curtis for another example.
So this one's coming from Purdue. You may have heard of it before, course signals. The purpose of course signals is to be able to tell a teacher which of their students are on track for success and which may be at risk for failing the class. It's something that runs on the learning management system, and so faculty have to go and actually perform a request for the report. So they put in a request, and it comes back with this traffic light report with all their students. Students under the red light have a high likelihood of failing. Those with the yellow light might have a problem succeeding, whereas those with the green light are on track for success. And they're able to do this. They built an algorithm based on a lot of different variables coming from a lot of different data resources. They look at the percentage of points earned in the course to date for just the students in that class. They look at the interaction that's going on in Blackboard, Vista, compared to other students in that class. So it might be the amount of time they spend on a page or how many clicks. We also look at prior academic history. So this is coming from the more administrative level, GPA and standardized test scores. And then some basic student characteristics, age, credits attempted. And these variables are able to help them identify which one of these classes students might belong. Whether the teacher should be spending more time with these students or with these. They looked at retention rates when they started using course signals, and here's what they found. These are the students who did not use course signals at all or had a class that used course signals, and after 4 years their retention rate had dropped down to 70%. But those students who had a course, one course at least that used course signals, after 4 years their retention rate was still up at 87%. 2 or more, they saw 93%. Obviously the group sizes are different, but making a difference, helping teachers identify where to spend their time, and it's bringing back good results. Charles.
I heard, and I don't know, maybe you've read about this or know more about it, but I heard that someone kind of debunked this. What they determined that the correlation really had to do with whether someone had taken not at least one course with course signals, but if they had passed one course at all at the university level, whether it was with course signals or without course signals, that was the predictor as to whether they would succeed.
Yeah,
So
I've
the
seen
ones
that.
who didn't succeed didn't even make it through that first course.
Oh, okay.
But I don't know for
Yeah.
sure, but I heard that from somewhere.
Huh.
Be worth looking.
Yeah. When you look at the cohort size, 5,000, you think there'd be more than 5,000 students for that first year. Anyways.
So, this is interesting to me because I think that the tool is obviously a very powerful one, but I think it really leads us into the trap of thinking that we are causing students learning. And have there been done any experiments with putting the tools in the students' hands? Putting that data in the students' hands, the guys who,
Yeah. Course Signals
according to
app
me-
also sends the report to students, or at least the teachers can have the report emailed to that student saying, hey, I noticed I did this report and we found this about you. What are you gonna do about it? You wanna meet?
There is a good example that Susan's asking for, and it was developed back in the 1970s. It was called the ticket system. It was developed here on the BYU campus by IP&T faculty, Vic Bunderson, Dave Merrill, and others. Let's see, I was a graduate student here then, and Russ Osgothorpe was at that time, and some others. And the idea of the ticket system was that the student didn't get anything unless they asked for it. And it had a specially designed keypad over here where they could ask for a new objective, they could ask for the rule for that objective, or they could ask for examples, easier or harder. And they found that the students did well in that system. As a matter of fact, the ticket system is still being used on the BYU campus, the only place in the world where it's still used. But it was an example of what you're talking about, Susan, and it was liked and it was successful.
so just, data is data, but putting it in the hands of the people,
Yeah.
I think that what qualitative people like me are nervous about is this proposition underneath that we're causing student learning and there are objects and we're getting all the data we can on them because we're gonna do something and then but I think you just put the data in their hands and something very different happens.
Yeah.
There's
It's a
assumption
very
there.
different assumption.
Yeah.
There's a difference between causing it and facilitating it. So, and you have to be careful of the developmental age of the child too. Giving a bunch of data to a 7, 8-year-old isn't gonna help much. But facilitating them and knowing something about the child is, the teacher facilitates the learning by knowing something about the performance. That's really important to do. And yeah, we do need to know that student learning is caused by the student, not by us. We facilitate it, we put them in an environment that's going to foster or improve that, but we have to be careful. Now, as adults, it would be nice to have information, and then we can use that as agents to do what we're going to do, and it would work better for
When you
them.
get agency, when you're 7 or 9.
But being able to analyze that data is also different, right?
Maybe you get agency at 8, that's really bad.
But I think the point is that the data that's produced, or the analyses that are produced from this, can be used by a number of different agents. I mean, it can be used by a system to change the learning path for a student. It could be used to give recommendations to the student themselves to act and change their own learning path. It can be used to be given to an instructor to help a student change a path.
Help self-regulate
Yeah.
themselves.
So I think it can be used in any of those
Or for a designer too,
situations.
identifying what parts of their design are not working out so well.
I mean, the fact is, learners are collecting data all the time. It's just a different kind of data, right? It's individualized, maybe somewhat eclectic or idiosyncratic data.
Another example I wanted to share was using social network analysis to learn more about how we learn and what's going on in at least online courses. So there's a study done by McFadyen and Dawson. They looked at discussion board interactions between students on Blackboard. They looked for communications between individuals, so they counted who was reading whose posts and who was replying to who. And then they analyzed by grade. And here is what they found. They produced some social network graphs. This is a high-performing student, and this is a low-performing student. And what they found is that higher-performing students, in the color of red, tend to have a lot more interactions than lower-performing students. But they're also interacting with more higher-performing students, whereas the lower-performing students in yellow tend to interact more with lower-performing students. And so this can give some ideas about how students are engaging in a course, not just in frequency, but in quality. Why are the lower-performing students tending to just relate to these other lower-performing students?
So if I tweet more, my grades will go up?
Yeah, exactly. That's the other problem.
If you're tweeting with the right people.
Yep.
That's what this says.
And if tweeting is interaction.
The guy that I'm tweeting has the answers to the test.
Extracting meaning from those numbers is a very complex process.
Yes, it is.
Just wanted to end on some of the projects that we're involved in. I'm working with Charles Graham on projects where we're trying to learn more about how learners engage with online or blended learning. Our bigger goals are to be able to identify those students who may be disengaging, but then also looking at when are they disengaging and what's leading to that engagement. And this can obviously, as we've been discussing, be an evaluative tool to the instructor or to designers to pinpoint where problem areas might be in learning. But then it can also be a learning personalization tool. Here's some of the things that we're interested in. We've got engagement, desired outcomes, which can be performance or learning. We have learner characteristics and the learning experience. A lot of research has been done on this relationship here between engagement and desired outcomes. So researchers have found that more engaged students tend to be more satisfied, to perform better. But what we want to do is expand from this research and look more at engagement in the context. And what is it that learners are bringing to the table when they come to our classes? And how do factors from our design of the course impact engagement? And we break engagement down into two types of engagement: emotional energy that students experience while learning, and then the mental energy that they're putting in. And we believe that different learner characteristics or the way that the learning experience is structured can impact these two types of engagement in different ways and then lead to different outcomes that we may be interested in beyond just performance. That's weird. With engagement, some of the data that or measures that we hope to use to collect data include some surveys, but we also want to look at log data, mouse tracking, experience sampling so that we can see how engagement changes across time, biometrics, which is looking at pulse, facial recognition, how you're sitting on a seat, but looking at all kinds of information to see what is most useful to identifying those students who may be disengaging from a course versus those who are engaging. Some learner characteristics that we're interested in looking at: self-regulation skills, or the types of learning skills that students bring to the learning experience. Where we're interested in blended and online learning, what's their affinity to technology? Do they like using it? How well can they use it? What's their affinity to the subject? Self-efficacy, do they believe that they can succeed in this assignment or in this course? With the experience, we're interested in looking at not only delivery, did learning take place face-to-face or did learning take place online, but also the pedagogy, how students are interacting. Are they interacting a lot with other students, with the instructor? What are the interactions like? The types of learning activities that may be happening. And we're hoping that by bringing together all this information that we can begin to identify some of the meaningful relationships between what order did students follow to achieve a learning process, what activities did they look at first, how long did they do it, to be able to identify where are problem areas, that are causing disengagement, what learner characteristics may be leading to disengagement that we can do something about before they come to a learning activity. Anyways, there's a lot that we can do here. John, did you want to take a couple minutes? Okay.
I just had a quick question.
Go
Is
ahead.
that, are you looking primarily at K-12 or higher ed?
Higher ed is where we're starting.
Mostly because of IRB issues, which are complex at the K-12 level.
I'm just saying,
More
Christine, I
complex.
can hear the Alpine School District parents collectively screaming at the word biometrics in their children's.
Yeah.
You're not gonna love my child.
Yes.
Anyways,
And track if he's been studying.
this is our presentation. We hope that you can see that big data has a lot of applications in many different ways to what we're doing. To designing instruction, to evaluating, to helping the learner to learn more about learning, research. It's definitely becoming more big in education, and what we need are not only people who know how to do this type of analysis, but also people who know what's going on when we do this type of work and how to make decisions about it. Anyways.
Thank you very much.